Welcome to Brain Vision.
In this question, we have a blue supergiant star, which we want to compare with our own sun. Right. For this particular blue giant, its temperature is 30,000 at its surface. We want to find what is its principal wavelength, so basically the peak wavelength that it emits. We're going to find that using the Wien's displacement law. So Wien's displacement law states that the peak wavelength emitted by a blackbody is just equals to a constant divided by its temperature. So the constant that we're talking about is 2.9 times 10 power minus 3. It's in terms of kelvins meter. Right, we divide it by our temperature. Our surface temperature is 30,000 kelvins. We get 9.7 times 10 power minus 8 meters, which is about 97 nanometers. Now we know that this is in the ultraviolet range, right? Because it's smaller than 400 nanometers, which is the visible range, right? The smallest wavelength for visible range. So it's actually not in the visible spectrum, and therefore it would, since its peak is more biased towards the ultraviolet, therefore from what we observe, right, in the visible range will be mostly blue light, right, because it will have its peak near the blue region, and right, this will maybe be the blue region, 400 nanometers. So its actual peak is in the ultraviolet range, but of course it will have a significant proportion of its energy or photons with wavelength that is nearly 400 nanometers. So that's why we see it as blue. Now for the next part, we want to find what is the radius of the star, considering that it is about the 100 times, right, its power emitted compared to our sun. So the actual power of the star, we take 100 times multiplied by the power of our sun. Now we know that by Stephen-Boltzmann law, that this power, right, in terms of watts, is equals to sigma times the surface area times its temperature to the power of 4. So we know its temperature, we know the sigma, the constant, it's the first Boltzmann's constant. We can use that to find what is the surface area and hence the radius of the star, right? Because the surface area is just 4 pi r squared, right? So over here, the sigma constant is 5.67, that's 10 power minus 8. Area is 4 pi r squared. And the temperature is 30,000. So if you just divide all these constants over, right, 30,000 power 4 as well as this 5.67 and 4 pi, then we take the square roots of the entire expression, we should get r to be about 8.2 times 10 power of 9 meters. So this is the radius of the star. Of course, comparing it to the radius of our sun, we can take this r divided by r of the sun. We're given that the radius of the sun is about 6.96 times 10 to the power of 5 kilometers, so that's 10 to the power of 8 meters, and we get approximately about 12. So the star is about 12 times larger than our sun. Now, of course, the final part of the question is to ask whether it's correct to say that the visual luminosity is proportional to the total power. Well, in this case, it's not, because at such high temperatures, the peak of the wavelengths emitted is at the ultraviolet range. Right, most of the power irradiated is not in the visible spectrum, and as such, the visible or visual luminosity would not be proportional. Right, and the main reason is because of this, not in the visible region or spectrum.